In our first video here, we're going to take a look at an introduction to improper integrals. Sorry, I did a crazy scroll there. So what we're going to start with is taking a look at sort of our most basic type of improper integral, starting at 1 for our limit of integration and going to infinity. So of course, this is going to be a little different than what we're used to because usually our limits of integration are numbers. Infinity is not a number. This is saying for us to just keep going forever and ever and asking what happens to this integral in with an integral like this. It's a definite integral, and our question is is this going to be equal to a number, or is this area just going to keep getting bigger and bigger and bigger as we go to infinity? So what we're going to start with is taking a look at a similar integral. So instead of having infinity up as our upper limit of integration, we're going to have t. So that's just standing in the place of any number that's greater than 1. And so we would take the integral like normal. So, this is the integral of from 1 to t of x to the negative 2 dx. And we use our power rule and we add 1 to our exponent. And so we are going to get, let's see here, plugging in t, we're going to get negative 1 over t, then minus negative 1 over 1. So simplifying this a little bit, making it look a little nicer, we get equaling negative 1 over t plus 1. So basically what that's telling us is that as we go finding the area on this and having t get larger and larger, this is an equation that we could use to find the area. So here's a picture of 1 over x squared, and there's that area that we just found. So for example, if we wanted to know the area from 1 to 5 of 1 over x squared dt, we just found a formula for it. We could do this as 1 minus 1 over 5, and we would get 4/5 would be the area if we went from just 1 to 5. So again, the question is as we get more and more area there, what's happening here? If we, go out a little further and keep adding more and more area, is our area getting equal to a single number, or is it just continuing to get bigger and bigger and going to infinity? So what we want to look at is really actually what is the limit as t goes to infinity. And we remember we found this integral. We just found it. And it was 1 minus 1 over t. So this is really what our question is what is the limit of this expression, 1 over 1 minus t? And sorry that my handwriting is so bad here. Let's make it look just a little bit nicer. What's happening as t is getting larger and larger and larger. And it may be a little while since you've done any limits like this, but thinking back to what we do in 251, as t gets larger, this fraction gets smaller and smaller, and it's actually going to get closer and closer to 0. So in our sort of math language, what we often do with this is we write that this is going to 0. So we draw a little arrow through it and put that that's going to be 0. That as t gets bigger and bigger and bigger, that's just going to keep getting smaller and smaller and smaller. So this means that our limit is going to be equal to 1. So what this tells us actually is that the integral from 1 to infinity of 1 over x squared dx is actually equal to 1. That as we go out to infinity, we're subtracting less and less off that area, and we're actually going to have a whole area of just 1. So let's take a look at another example, sort of similar, but kind of the other way around, looking at this function x times e to the x, but instead of, 0 to infinity, we're going to go from negative infinity to 0. So again, we've got this situation where we've got this indefinite integral, and instead what we're going to look at is instead of going, starting at negative infinity, because that's not really a place to start, we're going to say what happens if we start at t. And we're going to have t going to negative infinity. And we're going to look at this integral of x times e to the x. So we need to take this integral first. So we need to take the integral from t to 0, and then we can look at what its limit is. And to take this integral, we have to use integration by parts. So in this one, we should let u be x. So we get du is equal to dx, and we should have dv equaling e to the x dx, because this is really easy to take the integral of both sides of. We get v is equal to e to the x. So our integral is x e to the x, again that's our u times our v, from t to 0, minus the integral of e to the x dx, again that is our v times du. And then we can take the integral of e to the x. I do need my limits of integration on there. So we get x e to the x. The integral of e to the x is e to the x. And then we're looking at this from t0 to t, or t to 0, sorry. I always say that the wrong way around. It's so hard to do that. All right, so then plugging in our limits of integration, we're going to get 0 times e to the 0 minus e to the 0, then t e to the t minus e to the t. So kind of cleaning this up, we're going to end up with -1 here from this first part, plugging in 0, because 0 times e to the 0, that's going to be 0. And then our e to the 0 is going to be 1. So we're subtracting that, so that's where we get our -1. And then we're going to have minus e to the t plus e. So now what we need to do is remember to go back here and look up at this, our integral here. And remember, what we really want is to look at the limit as t goes to negative infinity of this expression, of this -1 minus t e to the t plus e to the t. So one of the things for us to remember, again, it's probably been a little while since you've thought about this in 251, but the limit as t goes to negative infinity of e to the t is 0. Remember, as that exponent gets to be a bigger and bigger negative number, that ends up being e1 over e to the t, or I don't like that variable being the same. We'll have 1 over e to the something. Maybe we'll write exponent right there. It's going to be a very big exponent on the bottom of that fraction, so we're going to get a smaller and smaller number. So this is going to get closer to 0. Again, you can also think about this in terms of the graph of this function. E to the x looks like this, and we're following along this graph going to negative infinity, and it's getting closer and closer to the x-axis, so its outputs are getting closer and closer to 0. So what happens with our limit is that this part's going to go to 0 and this part's going to go to 0. So even though that t is going to go to negative infinity, it's going to be multiplied by a smaller and smaller number that's going to 0. So it's going to go to 0 as well. So what we're going to be left with is just this -1. So that again tells us that our integral from negative infinity to 0 of x e to the x dx is going to be equal to 1. Oops, excuse me, -1. So this one does converge, as did the last one. Not all of these converge. We will see examples in class where things do not converge. So I just want to make sure that we don't start thinking that all of these must converge because these two examples do. That doesn't always happen.